Swayam Prabha. Digital India. Educated India.
So, welcome to this final lecture of this course on computer organization and architecture. In this lecture, what I will be doing is I will be talking about some of the recent trends in computer architecture, why certain things have happened in the last decade and a half, and then I will also be giving you some, I will be showing you a video basically from Google on YouTube on what is the next computing trend in computing that the world is actually headed towards before we sum up this course. This is the computer made in 1946 in University of Pennsylvania, which is measured in cubic feet, and this was not bigger than today's glorified calculator. The functionality that this could execute was very close to what today's calculator can do. This was basically called the ENIAC. It had it had several vacuum tubes and several connections that were going on, lot of wires that were running, and the same chip, the same ENIAC with the same functionality in 1997 was basically built using 1,74,569 transistors, and the size of the chip was 7.44 millimeter into 5.29 millimeter, and it was using a 0.5 micron technology, 0.5 into 10 power minus 6 meter technology. What is 0.5 micron? In the sense that if you assume that a transistor, it is a very rough answer. What do you mean by 0.5 micron? The rough answer is that if you assume a transistor is a square, then the side of the square is 0.5 into 10 power minus 6 meters. So, this is roughly what we can say. Now, what made this possible? That is from this in 1946 to this in 1997, so 51 years, what was it that made it possible from cubic feet to less to a couple of millimeter square? The first thing that we should note is the major integrated circuit revolution, which came in 1958 from Jack Kilby of Texas Instruments, where he showed that on a same substrate more than one component can coexist. So, he made one substrate where it had 5 components, it had a couple of transistors, resistors and capacitors, all of them existed on the same substrate, what you see on your left hand side in your screen. So, this basically that means that I could get the circuits, different components of the circuit put on the same substratum, and that formed the basis of what we call as an integrated circuit, where we integrate multiple varieties of components, different types of transistors, etc., on the same substrate to realize certain functionality. That integrated circuit revolution had grown so well that in 2000, what you see, these are some of the images which Intel releases. This is an Intel Pentium 4 processor in 2000, which had close to 42 million transistors and 1.5 gigahertz speed, and they were using this 0.18 micron CMOS technology, right. So, this is a 180 nanometer technology. So, from 1958, where we had 5 components on a substratum, we have gone up to 42 million components on a substratum, and this is the basic integrated circuit revolution. So, what happened because of this integrated circuit revolution? The amount of money that we pay per million instructions per second, or MIPS, has decreased. Today, for 1 million instructions per second, we pay very less than, we pay almost zero cost. Okay. So, when you compare with 1975, for a 1 million instruction per second computer, they are paying $1,000. Today, it has the sub $1, right. So, this is the trend that you see. And what you see is there is a growth in the IC complexity in terms of number of transistors I put on a single chip. What you see on the left hand side, what you see on the y axis is a logarithmic scale, right. So, on a logarithmic scale, if I get a line, then essentially it is an exponential growth. And what has happened is that the number of transistors we could put in unit area has kept growing exponentially over the last several years, and that is what this has shown. This is showing. Now, if you actually count the number of transistors as second, this is the Intel released data. 4004 has less than 1 hour, that means they are less than 3600 transistors. 8080 is about 2 hours, while you take the P4 which is around 1.5 years. So, number of 1.5 into 365 into 24 into 60 into 60, that many seconds, that many transistors were there in P4 as you see here. And when you see the comparison of sizes of the die, please note that the die size has not grown very big, but the number of transistors that we put inside a die, that is transistors per unit area, has significantly increased, and that is the integrated circuit revolution. Now, how small are the transistors? We have seen something till 2007 where we are seeing it is sub 0.03 micron. Okay, so you know that you may know that the human hair, a well maintained human hair, the diameter of a well maintained human hair is 56 micrometer. Now, you see something that is 0.03 micrometer. So, that is the size of transistor today. So, one of the important things, one important law that was basically predicting this was the Moore's law, which basically said that the transistor density will double almost every 2.3 years. What it means that the number of transistors I can put in a unit area will almost double every 2.3 years, right, and that is what we have seen. So, that doubling is what you have seen, the exponential growth in the number of transistors as you see here, right, within the same, almost the same area we were able to get twice the number of transistors than what was say 2.3 years before. Now, if I have more and more transistors, what is the implication? Like, I have more workers, right, every transistor can implement some functionality. So, if I have more and more workers, that means I have more functionality, and that means I can put more complexity into the system. The other way of looking at it, more and more transistors, it becomes very complex to manufacture, complex to verify, and if I put more functionality, your complexity of the chip will increase. So, I can do complicated operations, complex operations on the system, at the same time the design also becomes complex. So, all these things will have an implication on the cost of manufacturing the system. On the other hand, the frequency also started doubling, right. So, this means that I could get more and more fast clocks, and assuming that the number of operations remain the same, number of cycles per operation remain the same, if I have a higher frequency, then I can start executing instructions faster than the previous generation. And again you see a log scale on your y axis here and a linear growth in the frequency, which just means the frequency was growing exponentially over time. Nothing comes free of cost. As your frequency started increasing, your power also started rising exponentially, the power consumed by your processor. So, this is what we see, we have already seen a hot plate, and if that trend had continued post, what you see on the y axis is again a log scale, which is having power density, which is the watt per centimeter square consumed by the chip or dissipated by the chip. So, now because of that your temperature starts increasing. So, if you had allowed the trend to continue, we would have reached a nuclear reactor by some around mid of 2000 to 2010, and then a rocket nozzle by 2009, and almost you would have get sun's surface by 2010. So, this is very complicated because as your frequency increases, your power consumption also increases, your power density, amount of power consumed per centimeter square also increases, and that can reach to lot of power temperature issues, and this is something which we cannot even imagine. So, we can maximum go up to a hot plate, and that is where the things have stopped. As you see in the graph, it all stopped at P6 Pentium, where we have touched a hot plate in terms of temperature dissipation. So, what can we do to bridge this gap? We can increase the frequency, we can increase the voltage of operation, we can increase the amount of work done per time unit. These 3, and we can increase the number of hardware units. These are the 4 different ways by which I could make the computer more and more faster. If I start increasing the frequency, already this has been attempted for a long time, the increase in frequency need not necessarily give you a better performance. So and increasing the frequency also increase the power consumption. If I increase the voltage of operation, certainly your power also gets increased by large quantity. So the best thing is to increase amount of work done per time unit. So that is how many companies including Intel came out with the notion of multi-threading or hyper-threading. In a multi-processor system, there will be 2 separate CPUs, each will have its own architectural state, meaning the general purpose registers and all those things that you need to run the process. They will have 2 separate architectural states, so they can run 2 independent processes. But one of the biggest drawback, as you would see in the subsequent slide about this, is that if one of the processor, whatever you see on the left hand side, there are 2 processor execution unit with 2 architectural state registers. If one of the processor is executing an integer program, the entire floating point resource that you have put on the one of the processors is going to be waste, while the other processor, if it is going to use floating point programs, then the integer arithmetic there is going to be waste. So I could have 2 classes of program, one using floating point, one other using integer arithmetic. When I put, so if in the case of the multiprocessor that you see on the left hand side, both the processor will have both the floating point and the integer unit. So one processor, when it is executing the integer program, the floating point unit will be idle there, and another processor, the integer unit will be idle. So in sense we are not using, we are not effectively or efficiently using the hardware given to us. So that from that multi-core, that's why there is a notion of hyper-threading which was introduced, wherein there will be 2 different architectural state, but the processor execution resources will be shared. That is what you see on the right hand side in this slide. So what happens here is that in the context of me having one integer program and one floating point program, there will be 2 different architectural state, of course, for each of these processes, but the processor execution resources will be more effectively used because both the integer and the floating point units that are part of the right hand side, the single processor execution resource, will be effectively used here. So from going from a multiprocessor to a multi-threading or hyper-threading environment, this served as a basic motivation. Not every program will go and do every type of computation. There will be some program which will do integer, there will be some program which will be doing floating point. So if I have one processor execution resource which will have both integer and floating point, I could run multiple processes at the same time. This is the biggest motivation for people to start looking at hyper-threading / multi-threading. So this is a very clear thing, whatever we see. So this is a graph actually. Whatever you see on the y axis is the time, and whatever you see on the x axis is whether a particular unit is occupied or not. Okay. As you see, the first, we have already seen a superscalar. Now in the first cycle there are, let us assume there are 3 units inside the superscalar processor. Now in the first cycle 2 of the units are occupied, 1 is empty. In the second cycle all the 3 are empty, in the third cycle 2 are occupied, etc. I am showing on the leftmost side of your thing, just superscalar. Now only one process, the orange process, as I see here, maybe you see it as yellow, something yellow orange type works here, and only one process can execute. When I have a multi-processing environment where I have 2 CPUs, as you see on the next from your left, the second from your left, I could run both the orange or yellow instruction and also the green instructions at the same time. Right. Now there is something called so this is 2 cores, one running one yellow process, another running green process. In the superscalar thing that you see on the leftmost, the first one, you can't run the green process until your yellow process is executing. Now if I have multi-core, if I have multi-CPU, I can run both the things. But what I have done, have I reduced the number of empty slots? Actually, by going from superscalar to multiprocessing, I have doubled the number of empty slots. Next comes the the hyper-threading. where we can start using some amount of resources, right. So, the hyper-threading basically has two architectural state as I shown here, but the execution resource will be shared. So, what you see on the third column, that is under hyper-threading in this slide, you see that whatever we saw as multi-core, the execution resources have merged there. Now, you see the number of white squares on your third column is much less. Now, today we are looking at multiprocessing with hyper-threading, that makes much more sense, wherein you have a green, a yellow, orange and a blue and a yellow set of 4 type of programs. As you see, as you move from the left to the right, the number of white blocks actually significantly reduces, and this is one of the way by which I could get better performance for my workloads. So, a conventional superscalar, as we had seen, what happens, it takes one red program, executes it and finish, right. So, what happens is that if I do that, you see in this slide, as I move the mouse on top of it, you see there are many white slots here, these units are underutilized. When we move to the symmetric multiprocessing, where I have 2 cores at the same time, 2 different cores, the number of whites still actually doubles. So, I have more hardware and lot more hardware when compared to the single one, namely this. Compare this, only these slots are wasted, but here it has doubled, this slot plus this yellow slot. So, when I go for symmetric multiprocessing, yes, I can do 2 processes at the same time, but then the wastage of resource is still comfortable. The wastage of resource is still significant here. So, that then came the notion of a multi-threading, as you see here. So, I have 4 types of programs in the RAM as I show through the mouse, one green, red, yellow and purple, and in multi-threading what we do, we just first execute 2 of these 4 threads, let us assume. So, the red and the yellow gets executed, but what happens is at one time slot, as I move, every row in this particular front end, as I show here, will have only either the red instructions or will have the yellow instructions. By this, what happens is that the number of wastage of units does not significantly reduce. So, this is multi-threading, where I have a single CPU and I execute 2 threads at the same time, but every entry of every thread will occupy exactly one. So, every row here will not have more than one instruction or more than one process that is basically involved. So, in one slot I will have either the red or the yellow, but not both. That is what we call as multi-threading. Now, when we go to hyper-threading, please note that in one slot I could have both red and yellow instructions. So, the yellow instructions will work and there. Now, immediately you see that the number of white spots here have reduced. So, this is how processors got evolved, say till last 4-5 years, wherein we brought in a notion of hyper-threading, multi-threading, etc., basically to start utilizing the resources. Today I can't keep increasing the frequency, because if I start increasing the frequency beyond this point, your system will start burning. We cannot take that much amount of temperature. So, the idea is to have slightly low frequency or very low frequency CPUs, but many of them. So, if I have one say 4 gigahertz CPU, but I have 3 1.5 gigahertz CPU, then certainly that 3 into 1.5 is 4.5 gigahertz. If I am able to use those 3 CPUs, underlying 3 CPUs effectively, then automatically that will overshoot the 2 gigahertz circuit. The question that we want to do is that given a hardware with a limited frequency, but multiple of them, how can I use all of them together to go and exploit the performance? And that is what the last part of the course before this lecture, I gave you the notions of different parallel random access memory, like your EREW, CRCW and CREW, which basically teaches you how to write programs so that things like hyper-threading can basically get a full a set of threads, so that it can process it faster and you get the best benefit of having such type of an hyper-threading environment. So, with this, this is how the superscalar and desktop level processors are going. So, to conclude, what video says is something much different than what we covered in the course, but that is going to be the future of computing. So, what is needed is a completely low, very low power embedded processors capable of doing certain minimum functionalities in terms of graphics processing, in terms of communication, and in terms of embedded computing. That is one major need that we have, and we can't say that the processors that could basically achieve what the video showed could be small computing systems, because the type of processing that has happened there essentially needs lot of computing power, but that computing power may not come from a general purpose system, but it will be custom made processors with certain digital signal processing, vector processing capabilities. So, how do we get to this level is going to be the next quantum jump in the field of computer organization and architecture, and that is going to be a very interesting revolution that is going to happen in the next few decades, and it is going to be pretty interesting. So, computer organization and architecture will never have its death. We have to, it will grow, and it will grow in phenomenally in different directions, and this one what we saw in the video is certainly one direction in which the next generation computing processors have to look at. With this word, I conclude this course. I hope you enjoyed this course, and I look for feedback from you and more interaction and a good career hopefully in the area of computer architecture and organization. Thank you very much.